right, so packets, sample 1, sample 2, we got just a very short amount of time here to do one if you want to look at it. Anybody got one? On sample 2. Alright, so sample 2 gives us this area, gives us the curve 1 over x, and they tell us what the area is. Okay, so what would be the integral that would describe that area? Integral from 2 to k of 1 over x dx, right? So how would we do that? Antiderivative is ln x, right bracket, 2 to k. Put in k, ln k, which we know k is positive from the picture, so I really don't have to worry about the bars, minus ln 2, and I know that equals what? ln 4. So ln k would equal ln 4 plus ln 2, right? Now, many times I've told you that in the no calculator multiple choice section, they love testing you on algebra, trig, exponentials, and logs. Especially logs, we have trouble, which I think is our issue right here. Because what can I do with that right-hand side? That is ln A. So k is 8, right? Because the property of log says if you add 2 logs, you can multiply them, or if you have a multiplication, you split it into division. Likewise with division. Okay? So you can know everything in the world about calculus and get down to here, and then it's the pre-calc stuff that gives us. Okay, what else? We do it. We do it. Nothing? Same packet? Same thing. I mean, this, right? We're going to do the antiderivative, right? With respect to x. So you're going to raise that up to a 4, divide by 4, so 1/2 x to the 4th. Raise that up to a 3, divide by 3, so that, minus, so it'd be 1/3 k x cubed. Plus, now here's the trick part, I suppose, 2k. Now again, what's k? K is just a constant, just a number. So 2k is just like there was a 2 there. What's the antiderivative of 2? 2x. So what's the antiderivative of 2k? 2kx, right? The mistake people make is they want to treat it as a variable and raise it up like k squared or something. No, because 2k is just a number. So it's 2kx from 0 to 2. So I put your 2 in here, 16 and 8. Put your 2 in here, would be 8/3 k. Put your 2 in here, would be 4k. So it's f of b minus f of a, right? Now we're going to put our 0 in here. Now 0 is nice. It's 0, 0, 0. So that's all going to be just that. So we know that's got to equal 12. So we can subtract the 8 over there. So negative 8/3 k plus 4k equals 4. So this would be 12 thirds, so negative 8 thirds plus 12 thirds, right? 4 thirds K equals 4. So K equals 4 times 3/4. K equals 3. Right. So a little twist. Those did a little bit of a twist on our fundamental theorem part 2. But you can see a big part of the multiple choice is the part we've learned so far. Now, all of the free response questions we're not as ready for because those are more about applications of the integral. And that's what we're going to get into in chapter 7, especially. Well, we're going to talk about a little bit of it here. Because of, matter of fact, we're going to start with that here in about 5 minutes. Because a little bit of what we've, all the work we've done with derivatives, we can kind of just look in reverse and we can kind of tell some things about the integral anyway. But a lot of the multiple choice section is the basics of it, the skill part of it, the antiderivative part of it. So that part is what we've been working on. So
you did one up here too.
What's that?
You didn't
Okay. Well, yeah, this is a classic gateway right here. That's a U substitution. What would you let U equal? Tangent. Right? And the reason you'd let U be tangent is because the du is secant squared dx, and it's sitting right there. So that's your knowledge of derivatives. Derivative rules, you got that set right there, and that's on the inside, right? The tangent's on the inside. Now, the secant's on the inside too, but if I let u be secant, then the du is secant tangent, and that's sitting there, but there's an extra tangent that would be sitting there that wouldn't be any good. But this is going to be perfect. So that's going to sub out as my du, and then I'm just going to be left with u squared. So that's 1/3 u cubed plus c, and since u is tangent, that's 1/3 tangent cubed plus c. It's just, yeah. So that's definitely going to be in there. All right. Well, we better get moving on. So in your notes, so we got it. So the last thing we did was section 5.4. Okay, was the U substitution in the book. 5.5 is a section that talks about it's called integral aids, and different ways of doing integrals. Now, back in the day, before we had the fancy calculators here that would do it, and then of course you had computers, so you got to the college level, you get to research scientists and people like that would actually be doing complicated integrals, higher math. They would have fancy computers, but now we got fancy computers right here in our hand. But they could do it. But before that, it was tables. You looked up, you had integral tables. Now we don't have much of that version in our textbook. They've been rebound so many times we've lost a few of the pages at the edges. They have to cut out some pages to rebind when they rebind textbooks. So we don't even have them in a lot of our textbooks anymore. But have you guys been in chemistry? Ms. Larson or your chemistry teacher showed me, you heard of the CRC handbook? CRC, see, they don't even talk about that much anymore. But it used to be, you can get these huge books, or big, thick books. They're just full of formulas. They're just full of formulas. And scientists would use them all the time, and they would look them up. They had a big problem to do, like a formula to solve or an integral in this case. There would be a table, there would be 700 or 800 integrals. If your integral looked like this, then the answer to it was this, or the antiderivative was this. You had to look them up. There were just too many. Well, that's kind of what your calculator is. It's kind of like an electronic integral. And so we used to practice matching that. Because what you'd have to do is sometimes to get your integral to look like one in the table, you'd have to rearrange it algebraically. So it's a lot of algebra work, having to rearrange it to get it to match one in the table so you could solve it. Well, now we have these devices, so that's kind of taking that away. So we don't spend much time doing that. Matter of fact, I just skipped that section there. I think. I've been recording this. Thank you. I think. Yeah. All right. So that's 5.5. So now we got two sections to do here, 5.6 and 5.7. Okay, so we talked about the definite interval. When we started chapter 5, we said we want to be able to find this area. Remember when we first started calculus at the beginning of the year, we said there's two main parts. There's the derivative, rate of change, slope of a tangent line, and then there's area under a curve, which is the integral, the definite integral. The first 2 days of class, those are the two things we talked about, okay? And we've seen that play out. So the derivative, we went through all that, did all that. Now we, of course, made that connection now that area is related to derivative. It's the antiderivative. It's a reverse process. And that was the whole fundamental theorem part 1, right? The big aha, moment and so forth. But back to what we're really focused on here, the whole reason we're doing this connection, this study and everything is how do we find these odd areas? How do we find these integrals? Now we're going to learn that it isn't just about area. Matter of fact, we're going to do a problem from your packet. I'm sorry, I shouldn't. Some of you put your packets away. We're going to go back and look at a problem in the packet that you had and show how the integral can do it. And it really doesn't have anything to do with area. It's using this antiderivative connection here. But what have we done? So we said to do these odd areas. Well, one way to do it is it might make a geometric shape. Doesn't happen very often. So, we can do it, but it doesn't happen very often. Then we've spent a lot of time talking about this one, fundamental theorem part 2. Okay, and that's the key one because we can use the antiderivative. That's the connection to derivatives. So we can use the antiderivative. Well, that helps us do a ton of it. So we spent some time practicing doing antiderivatives. That's why we took the gateway test. We better be able to do some antiderivatives. However, there are some out there where you cannot do an antiderivative. Just can't. So the best we can do is approximate that area. Okay? And that's what we're going to get into today. Now, before I do that, and I probably should have done this first, but we're going to go back to sample 2, and we're going to go back, we're going to go to number 43. Nobody asked about it. I thought somebody might. Did you do this one already? Anybody? What'd you do? You did it?
Yeah, it's very simple. I don't have anything complex.
No. Let's try it, 20% chance. Tank is being filled with water at the rate of 300 square root of T gallons per hour, with T greater than 0 measured in hours. The tank's originally empty. How many gallons of water in the tank after 4 hours? What do you think? Not what do you think the answer is? What are you going to do to work it? Yeah, now you got 25% chance of getting it right. It's 0 to 1, maybe 1. Do what? Where are you getting 600? Put the 4 in for T. No. Because that's gallons per hour. Doesn't it make sense that this is a rate? Couldn't we call that F prime maybe? Now why we would call it F when we're talking about gallons, so maybe we should call it G prime. Right? Doesn't it make sense that that would be G prime would be 300 T to the 1/2? Doesn't that make sense? Gallons per hour. But we want to know what? Gallons. Don't we want to know G of 4? Isn't that what we want to know? So how in the world could we get G if we know G prime? Do the antiderivative. So we raise that up to 3/2, divide by 3/2, which would be 2/3. That'd be 2/3 times 300, T to the 3/2, plus some C, right? So that's going to be, what, 100? So this is going to be 200 T to the 3/2 plus C. Isn't that what G is going to be? Now, what else? I have an initial condition. What do I know? So give it to me in math notation. G of 0 is 0. So I'm going to put a 0. So what's C? C is 0. So G is 200 t to the 3 halves. So what's G of 4? 200 times 4 to the 3 halves. So the square root of 4 is 2. 2 times 2 cubed is 8. 8 times 200. 1,600 gallons. Right? That's not hard, right? We could have done that a month, 2 months ago. I think. We talked about differential equations, right? We know about rates, what we know about derivatives, gallons per hour, but we want gallons, so gallons per hour is a derivative. We want gallons, so that makes it. We talked about distance travel. We talked about total distance travel. And I give you a velocity equation, right? How far do we travel? We got to do the antiderivative with a plus c. We got initial, right? That's not new. That's not new. Okay? So that, a month ago, before Christmas maybe, right? We talked about differential equation. Maybe it was right after Christmas, whatever. So that, to me, that one's not, that one's probably one we should have done on the midterm. To be honest with you, I probably should have circled this one, right? That could have been on the midterm. This is basically a differential equation with initial condition. It's an initial value part. Okay? This is the new part that I want to show you right now. You may remember that there have been several times I've told you over the course of this when we're doing these packets where I've said, hey, if you do, we can do this problem, but it'll get easier when we learn some other stuff. Okay? Well, here's what we're going to focus on now going forward. That the integral, think about this now. The integral of f prime, according to fundamental theorem part 2, is what? F of b minus f of a, right? Now think about that. A and b are the endpoints, and let's say f prime is a rate. So f prime is a rate, gallons per hour, right? So f prime is gallons per hour. Then what's f? So isn't this gallons when? Gallons when? Well, no, just B. Gallons when? Not in this problem. Just in general. Gallons when? At the end, minus gallons at the beginning. Right? So this is gallons at the end minus gallons at the beginning. What's that? How much what? No, that's not how much you have now. This is how much you have now. This is gallons at the end. No. You're getting closer. Gallons at the end minus gallons at the beginning. The net change in gallons. Net would be the word, not gross. The net change in gallons. Right? Now this one, what were the gallons at the beginning? So they were the same. So gallons at the end is the same as the net change, right? We started with 0, we ended with 1,600, so how much did it change? 1,600, but those aren't always the same, right? If the tank wouldn't have been empty, right, then the gallons at the end is not the net change in gallons, right? So that just gave us a really important thing. Now, this is not that important for right now, but down the road. So what we just realized is if I do a definite integral of rate of change, that's going to give me net amount of change. You got it? Okay? That's a really important thing right there. And guess what? Doesn't have anything to do with area. That didn't have anything to do with area. Right? Nothing to do with area. So the definite integral has now just become a much more powerful tool than just to find some area. Because in the past, you might have been thinking, well, we want to find these odd-shaped areas. How often do I need to find odd-shaped areas? Well, this is a whole different deal. This is saying that if you do the definite integral of a rate of change, it gives you the net amount of change. Okay? So in this one, we could have done, so we have a rate of change right here. So we could have done the definite integral of 300 t to the 1/2 dt, right? And so let's do that. So the antiderivative of this we found out is 200 t to the 3 halves, right bracket 0 to 4. So we put in a 4, we get 1600. We put in a 0, we get 0. The net change was 1600. Now, but do you notice what it is? That's how many gallons at the beginning, or at the end, minus gallons at the beginning. That gave me the net amount of change. Now, since the tank was initially empty, I know that's how many. But so we got to understand, is that what it asked? Did it ask for the net amount of change? No, it asked for the amount at the end, right? How many was in there after 4 hours? So that's actually the 1600, right? But this gives us, but we can still figure it from that, okay? So understand, that's 2 different ways to really approach it, okay? Now, here's where the real power of this is going to come in. Go back to that screen I had just a minute ago. When you have a definite integral, sometimes you can do the antiderivative and sometimes you can't. So we're going to learn about approximating definite integrals in case we can't do the antiderivative. So if our rate of change is something we can't do the antiderivative of, we wouldn't be able to do this. We'd have to do an approximation. We could still get this answer. Could you do the red method without being able to do an antiderivative? Could you do the red steps without an antiderivative? No, because you wouldn't be able to get G. If you can't do the antiderivative of G prime, this method over here doesn't work. This would, because we can find this definite integral by an approximation technique, thinking of it as an area. That will work. This would. So this has great power over that method that we were doing before. Okay? Anytime we're dealing with the rate of change. All right, so that's looking ahead a little bit on what we're going to do, but that's a really key concept. All right, back to this. Okay, so now we're going to dial in and focus on approximation. So if I have a definite integral and I want to approximate that area, what's it look like? So let's go through this one right here. Write this, draw this in your notes. You're going to be drawing a lot of pictures and you're going to be writing a lot of stuff out. So you got to quit being lazy, right? When I look at a homework tomorrow, I'm going to, the only people that I would even feel remotely a little bit of, okay, I can see why you didn't get your homework done is if you go to Millard South and cheer us on in the district final tonight. Then if you're there tonight, come up and see me and I might give you a break on the homework. But other than that, I'm going to be coming around looking at homework tomorrow and I'm going to see a bunch of pictures on your paper, okay? And I'm going to see a bunch of drawings, a bunch of rectangles, a bunch of stuff written out, okay? So all these days, this is not one of those days where I say, hey, do these in the packet and you do them to you. Or you do them during class time and then go do them again. Or I say, hey, work a bunch of antiderivative practice problems for the gateway test. And then you do like 4. Okay? All right, so this is number 17. You're going to do one very much like, one of your homework problems is going to be very much like this problem right here. So we want to find this area. Now we know we can do an antiderivative very easily. We can do f of b minus f of a, right? We're just going to show on some we know how to do. Matter of fact, I probably should show you this. Here's the point. Here's the point right here. Okay? If I get on my calculator and I do the integral of from 0 to 2 of sine x dx. My calculator does that. Why does it do that? How does it get it? Fundamental theorem part 2. The calculator is smart enough to do the antiderivative of this, and that is an exact answer. Now, if I wanted the approximation, I could go control enter, I could get a decimal. But that is an exact answer because it can do the antiderivative. If I change that just ever so slightly, and I go in here and I make that x squared, look what my calculator gives me. Why? Because it can't do the fundamental theorem part 2 because there is no antiderivative of sine of x squared. So the calculator is doing an approximation technique to get it accurate out to a whole bunch of decimal places. So this is exact out to probably those 12 or 13 decimal places. But that's why it's giving me that answer right there. Okay? All right. So how would we do an approximation technique on this one right here? Well, on number 17 in your book, it says, this is on page 355. It says, draw a sketch that illustrates the approximations L4, R4, M4, and T4. Okay? Then compute each approximation and compare it with the exact value of the interval computed using the fundamental theorem. Well, we can do the fundamental theorem right now. Fundamental theorem is 1/4 x to the 4th, negative 2 to 2, plug in a 2, 16 times 1/4 is 4, minus, put in a negative 2 is also 16, 4 minus 4 is 0. Does it surprise you that that area is 0? No, you knew it was going to be 0, didn't you? Okay, so we know the exact answer is 0. Now, so we're going to compare, so that's the exact answer. Now, they want us to do L4, R4, M4, and T4. What in the world are those? Well, here's where you need your calculator. So, I'm going to send you this right here. Okay? And I'm going to send you this. Okay, and I want you to open this one first, the one that says LRAM, RRAM. Now, you're not going to have to do a whole lot with these, but you have them. Did everybody get them? Okay, and you might have to go to the home screen to find it in your documents. So the one that says LRAM, RRAM, all right, we got to move along here. So if you control and right arrow, control and right arrow, control and right arrow, okay, you get to this picture right here. So control right arrow, control right arrow, control right arrow, you get to this. Okay, now it's a little easier for me on the computer to do this. But basically what we have here is, see this LRAM. Now what's that stand for? It stands for Left Rectangle Approximation Method. Left rectangle, you don't worry about it, you don't have to memorize that, but these are called 4 left rectangles. Now we started, that was the day you had to watch my video actually. And I went through and I drew some rectangles and we did some stuff with some velocities and that kind of thing. But if this is the function x squared plus 1, and I wanted to do the area from 1 to 3, right? One way of approximating that area would be put some rectangles under there because I know how to do rectangles. Okay? Now, it's going to be short, right? It's not going to be enough, right? So what if I had more rectangles, right? Oops, go back. Okay? What if I had more rectangles? That'd be better, right? But what we want to do is just understand, how do we draw a left rectangle? So there's 4 left rectangles here. We got a distance from 1 to 3 that's 2. So how wide is each rectangle? Well, each rectangle is going to be half, right? 2 divided by 4. So you're going to have 1 to 1.5, 1.5 to 2, 2 to 2.5, 2.5 to 3, right? So they're going to be a half wide, and then this one is how tall? Well, at 1, if you plug that into the function, 1 plus 1 is 2. So this is 2 tall, half wide, 2 times a half is 1, right? This one, you plug a 1.5 in, now it's going to get into decimals and stuff. We see these numbers here. So anyway, that number is going to be too small. What would a right rectangle? RRAM, right rectangle approximation. So look what we did here. We still divided it up into 4 subdivisions, but this time our right edge of this, we're going to call these, there's going to be a lot of terminology today. This is called a subinterval. Our interval is from 1 to 3. We divide it up into 4 subintervals, okay? And so here, the right rectangles mean we take the first subinterval, we go to the right edge of that subinterval, and we go up to the function, and we let that be our rectangle height. So our rectangle width is down here, and our rectangle height is our y values, right? So rectangle height is our y values. That's a key concept. So I plug 1.5 into the function. So notice that area is going to be too big, right? That's too much. That's going to be what we call an over approximation, whereas the other page was an under approximation, right? Okay. So that's left rectangles, right rectangles, and then you've got midpoint rectangles. Now midpoint rectangles, you notice, might be a little better. That's kind of a compromise between those two. So with midpoint rectangles, what we do, again, we have 4 subintervals. We take the halfway point, so between 1 and 1.5, that'd be 1.25. And we plug 1.25 into the function, and that gives us our rectangle height. So our width is still 0.5, and our height is whatever that function value is at the midpoint. Now that seems to give us a little over and under, and so that's going to be a better approximation, right? That's going to be a better approximation. Okay, and I think that's the last page. Okay, so just to get that picture in your mind, you guys are going to be drawing these pictures. Okay? We're going to be drawing these pictures and calculating these areas. Okay? All right. So, another picture to show you. Okay, so here's an area from A to B. Okay? Okay, there's 4 left rectangles. Right? Left rectangles. Divide it up into 4 subintervals. Go to the left edge of each subinterval, up to the curve or down to the curve if it's down here, right? Might be negative. And then you go straight across, draw a rectangle. Up to the curve, draw. Up to the curve, draw. Okay? If you want to do right rectangles, they would be in the blue. There's 4 blue right rectangles. Make sense? Okay? Seems like it should be real easy, but sometimes it's a little confusing. Midpoint, we just do our same, divide it up into our 4 subintervals, and then we take the middle of each of the subintervals and we go up to the curve at that point. And here's the actual area right here. So notice this is better. This is closer. The right rectangle was too much. All of this over approximation here kind of offset this under approximation here. My left rectangles were a little bit too small. Had a little of over here, but had a lot of under approximation here. So a little too small. The midpoints were better. Okay? And then one of the things we talked about in that video you watched that very first day we did chapter 5 is trapezoids. So the other thing you can do is trapezoids. You can go to the left edge, you can go to the right edge, and you could connect them, and that would make a trapezoid. And that's kind of like a midpoint. It's kind of like a compromise, right? So it takes care of a little bit of the over, a little bit of the under, and that's a little better look. And then of course, but here's the real secret. The real secret is if we do enough of them, it doesn't really matter. Oops. How high do you go? Okay? Ah, dang it. I mean, you know what I mean? If you get enough left rectangles, you get a pretty good approximation, right? So even though midpoint's better, yeah, if you wanted to say, hey, if you do 100 rectangles, what would be better? Well, 800 or 100 midpoint rectangles would be better than 100 left rectangles, right? But that just meant, all that matters is how many decimal places you want to be, right? If you're going to do 1,000, if you're going to do 1,000,000 rectangles, it doesn't matter. You can do lefts, you can do rights, you can do midpoints. They're all going to, eventually they would get really, really close to the actual area, right? Now, who in the world would want to sit here and calculate by hand 100 rectangles, right? We're not going to do that. Our rule is going to kind of be this. If it's under 10, we're going to do it by hand, right? If it's single-digit subdivisions, we're going to calculate it by hand. If it's more than that, we're going to have a program, we're going to have a handy thing on our calculator to just type into, okay? But we're going to write them out by hand. Okay, so those are left and right rectangles. Okay, so let me, oops. All right. So let's go to, well, yeah, let's go back to your picture. So let's do blue. Let's start with blue. So it says to do L4. That's how we're going to abbreviate 4 left rectangles. We're going to call that L4. L4 is going to be 4 left rectangles, okay? And we're supposed to do R4, M4, and T4. We're supposed to write that out for number 7. And it says draw a sketch. It says draw a sketch, and then compute the approximation and compare it to the exact value. So I need 4 left rectangles. So let's go in here and draw it. First of all, we got to figure out how wide are they going to be. 1 wide. And why is that? Because our total width is 4, and we're going to divide it up by 4. Now, in general, that's called this right here. And we usually call that delta x for change in x. The width of our rectangles is going to be called delta x, change in x. Okay, kind of like rise over run, delta y over delta x, right? It's the run, basically. Okay, so we're going to divide that into 4 subintervals. So that's going to be 1, 2, 3, 4. Now notice it took 5 blue marks to divide that into 4 subintervals. Does that make sense? You start here, 1, 2, 3, 4 subintervals. 5 marks to do 4 subintervals. It's always 1 more. That's going to come in one of our definitions we write here in a little bit, so I just want to point that out. So 5 marks will give us these 4 subintervals, and they're going to be 1 wide. So my first left rectangle, we're going to go down here on the left edge to here. We're going to go over 1, and then we're going to draw to there, and that is going to be our first left rectangle. Right? Now, for sake of time, we're only going to draw 1 of them, but we're going to write out all 4 of them. But on your homework, when you do one of your problems is going to be similar to this one, you'll have 4 you'll have 4 drawings of this graph. Okay? If you want to get the homework points, you're going to have 4 drawings of this graph. You'll have 4 left rectangles on one of the pictures. You'll have 4 right rectangles on one of the pictures. You'll have 4 midpoint rectangles on one of the pictures and 4 trapezoids on the other. Okay? All right, so now, let's keep going. Next one. So we go to the next subinterval. We go to the left edge because we're doing left rectangles. And we're going to go to the curve and then across. And there's going to be our second left rectangle. Then we're going to go to the next subdivision. Where's the left edge on this one? What's the height? So sometimes we get no rectangle at all. I usually kind of draw it in there kind of thick just to show, hey, there is a rectangle here. It just has a 0 height. So it's going to have a 0 area. Okay, and then the last left rectangle is going to be there to there. Right? Now, let's draw that out. Write that out. Now, here's how you're going to do this. I want to see in math notation the area of each of those 4 rectangles. Okay? So, the first rectangle has what for its height? Now, how do you get -8? By putting a -2 back into, this is f of x right in here, by the way. Right? That's f of x. So f of -2 is what I want you to write. I want you to write it in f notation. Now, I know it kind of sounds like I'm making a big deal about writing this out, showing your work, not being lazy, and I am. But there's a reason. It's not just busy, right? Where we're headed with this is seeing patterns. We want to see patterns. And the more you write it out, the easier the patterns are to see. Now, times, what's the width on this? What's the width of this? 1. Now, it might seem kind of silly to write the 1, but I want to write it. Because when you look at this, and again, it's going to go to the patterns we're talking about, I want you to see height times width. Because I want you to see this and think of area. I want you to think of this as that blue area. So I want you to be thinking rectangle height, that's the f, that's the y value, and then rectangle width. Height times width, height times width, height times width is area. Okay, plus, what's the next height? F of -1 times 1 plus f of 0 times 1 plus f of 1 times 1. Notice we don't get all the way to the 2, do we? With our left rectangle, we did not have anything at the 2, right? We started at the left edge, we don't get all the way there. Well, that's because there's 5 of these marks, like I said earlier. There's 5 of these marks to divide it into 4 subintervals. We're only going to use 4 of them, so we don't use the one on the right. Okay, now let's do rights. Now I'm going to do this in green so we can see it, and then I'm not going to do the. Well, no, I will too. I tell you what. Let's don't do it in green. Let's do it in. We'll just do it in black. Okay, I'm not going to draw the right rectangles in there. Okay, but I will talk about them. The right rectangle. So here's your first subinterval. Where would we go to draw our first height? We would go here to the right edge, and we would go to the curve, and then we would draw backwards like this. Now, this is why you're not going to get to draw yours all on the same picture, because it gets too messy and you can't see anything. So you're going to have 4 separate pictures here. Okay? But that's how you do a right rectangle, is you draw backwards. So you go to the first subinterval, you go to the right edge, you go to the curve, and then you draw backwards for that. Okay? All right, so so what's my first height of my first right rectangle? F of -1 times width of 1. And then F of 0, because my next right rectangle is going to be here at 0. And then I'm going to go that way. Okay? And then my next one's going to be there. Here I said I wasn't going to draw them. It's going to get messy. But there's my next right rectangle. My next right rectangle, my last right rectangle will go up there and come down. And my right rectangle will be this black one here. Okay, so it's F of 0 times 1 plus F of 1 times 1 plus F of 2. So here I actually use the 2 because my last rectangle goes up here at 2 to that y value. So it's F of 2 times my width of 1. So this time I didn't use my left edge when I started with my right rectangle. Okay, M4. Now M4, where do I go? Where am I going to go to do this one? Right in here at -1.5, right? And I guess I could do that. I don't know. I don't want to use green because I don't do that for traction. So that would be, I would go to the curve, which would be about here, and then I would draw both directions. And then that would be my midpoint rectangle. So we go to our subinterval, we go halfway to the midpoint, and then we go to the curve. You always go to the curve for your rectangle height. Always go to the curve for your rectangle height. So there's our rectangle height, and so we draw both directions for our rectangle top, and then there is our midpoint rectangle. So that would be F of what? -1.5 times, what's our width? Still 1, right? The width, the subinterval width is still 1. That doesn't change. Plus F of, what's our next midpoint going to be? -0.5 times 1 plus F of +0.5 times 1 plus F of 1.5 times 1, right? Now, on our next quiz, I'm probably going to let you use calculators on our next quiz, but so then you can type these numbers into the function. Now, remember, the function is this, not this. This was the antiderivative. We always plug it back into here. The whole point of using this, because it's the area under little f, the whole point of using approximations is because when you can't do an antiderivative, right? So the only time we would do our antiderivative is if we're doing fundamental theorem part 2, right? Then we're not doing these rectangles. So we're always plugging it back into this function that's in here, little f right here. Okay, now the last one is T4, 4 trapezoids. Now what's the formula for a trapezoid? It's 1/2 the 2 parallel bases, right? Well, what would be our parallel bases? Well, it would be this side, and it would be this side, right? And then we would connect those. That's how you make a trapezoid, right? And we've done that already. We've done trapezoids like this. There's our trapezoid. Okay, so what is it? It's F of -2 plus, I didn't make enough room, f of -1 times, what's our width? Still 1. Plus, what's the next trapezoid? 1/2 f of -1 plus f of 0, and then all times 1. Now look at the picture on it though. Look at the picture on it. Now it's getting really messy, and that's why you're going to do 4 separate pictures. But here's f of 0, and here's f of -1. And when I connect them, what do I get? I actually don't get a trapezoid, I get a triangle. And sometimes that happens. Matter of fact, sometimes if your curve crosses the x-axis, you might have this edge here and this edge here, and when you go to do your trapezoid, it actually ends up being 2 triangles, right? So sometimes a trapezoid is a trapezoid, sometimes it's a triangle, sometimes it's like 2 triangles, right? Because one edge is up here and the other edge is down here, and when you connect them, you actually get that. But we still call it a trapezoid. It's still going to be this form, okay? All right, plus 1/2 f of, what's our next one? Notice how you reuse, right? The right edge of this first trapezoid is the left edge of your next trapezoid, right? You reuse those, except the ones at the ends. So f of 0 plus f of 1 times 1. And then plus 1/2, we got one more trapezoid, f of 1 plus f of 2, all times 1. And you notice that you use all of those edges, those 5 edges, when you're doing a trapezoid, because you use the left one, it's the left edge of your first trapezoid, and then f of 2 is the right edge of your last trapezoid, but you only use those once, the ones in between using it. Those are all the little things we're going to be picking up on as we go along in seeing these patterns. Okay? So once you have that written out, now you can easily just calculate those numbers. Let's just do the very first one. You're supposed to actually evaluate. So let's do the very first one. So this was -8. And then -1 cubed is -1. And then 0 cubed is 0. And then 1 cubed is 1. So -8 plus -1 plus 0 plus 1 is what? -8. That's clearly not 0, right? It's a horrible approximation. Well, 4 left rectangles usually is not a very good approximation, right? I mean, look at all this blue area we got here. These balance each other out. But then we got all this area up here that we didn't account for. So we got all this blue area that's way too much negative. And so, yeah, we don't get a great approximation there. But that's not what we're building for. We know a great approximation would be 100 left rectangles, 1,000 left rectangles, right? Well, even I'm too lazy to write out 1,000 left rectangles, right? Okay, so we're going to come up with a pattern, and we're going to come up with some formulas, and we're going to come up with a way we can do this, and we're going to show how the calculator was doing it for that one we talked about earlier. Okay, but this is an approximation technique and how we're going to write it out. So if it's under 10, if it says do an L8 or R5 or whatever, we're writing it out. We're writing it out just like this. We won't always draw them, but if drawing them helps you write it out, that's fine. But we're going to need to be able to draw them. On our next quiz, you're going to draw some, and you're definitely going to write out some. Okay, and you'll make it both on the same problem. Okay, all right. So let's go to that other real quick, to that other document I sent you. You don't have to pull it up right now. You can pull it up later. This is called, notice it's called Riemann. That's how you pronounce that, Riemann. A Riemann sum. It's actually named after a German guy, George Bernard Riemann. Okay? Now, this is very similar to that other one. The difference here is you can change how many you have. Okay, like if I want to do 4 left rectangles, fine. Or I can grab this slider and I can do more. Right? So it's kind of cool. So I can grab this slider and I can do more. And if I'd rather do midpoint, I can just grab this guy and I can go over here and I can do midpoint. Okay, and I can grab that and I can come over here and do right. And I can come over here and I can do trapezoid. Okay, then I can slide this and see how many I got. It gives me the approximation. So, okay, all right. So that's basically, that's it for that one. But it's just a way for you to visualize what these different things look like. Okay, so it's just a tool for you to use, okay, to look at those rectangles. All right, so you've got those two those two things. So now in our notes, we're going to write down this definition from Mr. Riemann. Okay? And this is called a Riemann sum. So what we just did there, those things we wrote out, where we added up those four rectangles, is called a Riemann sum. Now, there's a little technicality. A trapezoid is not a Riemann sum. A trapezoid is not a Riemann sum. Think R for Riemann, R for rectangle. R for Riemann, R for rectangle. Okay? Riemann is only talking about rectangle. Okay? A trapezoid is still an approximation technique. It's just not a Riemann sum technique. All right, what is a Riemann sum? All right, let the interval AB be partitioned into n subintervals by n plus 1 points. Now, you know why it says n plus 1? When we divide it into 4 subintervals, we had to use 5 points, right? So we can't call it x1, x2, x3, x4. If we're going to divide it into 4 subintervals, we got to start with x0. So A, our left edge, we're going to call x sub 0, and then x sub 1, and then x sub 2, then x sub 3, and then x. So on that last example we had those 5 points. We would call them x sub 0, x sub 1, x sub 2, x sub 3, and x sub 4. So that way our last one, if we're doing 4 subintervals, our last one is x sub 4. That makes sense. So the B is going to be x sub n, and, oh, I did that wrong. Gosh, how many years have I had that wrong? This should be x n plus 1. Should it? The one before x sub n should be x sub n minus 1, right? Like if that's going to be x sub 10, then this would be x sub 9. All right, so x sub 1 is to the left of x sub 0 is to the left of x sub 1 is to the left of x sub 2, dot, 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 is the left of x sub 9 is to the left of x sub 10, and then that'd be your right edge, your B. Okay, so that's all that means. It's just a bunch of language, mumbo jumbo, right? This is how we're going to divide up. This is the terminology we're going to use. All right. Let delta x sub I be the width of the ith subinterval. So delta x1 would be the width of the first subinterval, and delta x2 would be the width of the second subinterval, and delta x3 would be the width of the third subinterval, and so forth. Now, you might be saying, well, why do you need different delta x? Well, you don't have to have the same width on your subintervals. Now, 99% of the time, we're going to do that. Almost always, we're going to divide it up evenly. So if we got a width of 4 and we want to do 4 subintervals, they're all going to be 1 wide. If we got a width of 4 and we want to do 10 subintervals, they're all going to be 4/10, right? 0.4 wide. Okay? So almost always so delta x will just be our width, and it'll be equal all the way across. But it doesn't have to be. It doesn't have to be. You can have one rectangle be this wide, and one be wider, and one be narrower, right? Now, where that would really come into play is in the table of values. If you didn't have a graph or an equation, maybe you only had a table, you can't control how wide your interval is for your table of values. Maybe you have a value at 2, and then at 5, and then at 9, and then at 10, right? Maybe you got a 3 wide and then a 5 wide. You don't know. You can't control that, okay? So they don't have to be equal width. So delta x, basically I just say delta x is a width. Within each subinterval, let c sub I be the sampling point. In other words, that's the point we're going to plug into the function to get our height. So sometimes c sub I will be our left edge. And sometimes c sub I would be our right edge. And sometimes c sub I would be our midpoint. But it wouldn't have to be just those 3. We could pick it anywhere in there. You know what I mean? We could pick any point in the subinterval, go up to the curve, and draw a rectangle there. Does that make sense? We can draw one at the left edge, we can draw one at the right edge, we can draw one at the midpoint, or we can draw one somewhere else in it. Okay, now if you turn in your book to page 351, if you look at the bottom of page 351, you'll see what I'm talking about. you look at the bottom of page 351, and maybe I have that picture. Oops. No, I don't think I do. Do you see those rectangles there? See how some are fat, some are skinny? Right? So they're all different widths. And you see how, like, the first rectangle looks like it's about at the midpoint? See how the second rectangle looks like the height's right about at the midpoint? You see that? But what about the third rectangle? It's kind of at the right edge. The fourth rectangle's kind of at the right edge. The next one's kind of in the middle again. The last one's kind of in the middle, but a little past the middle. You know what I mean? But that's still a Riemann sum. That's 6 rectangles approximating that area, right? So, right, we don't usually do that, but it could be. So that's what all this is talking about here. All right, this sum right here, call it S sub n. S for sum, n is how many subintervals we have, right? So an L4 n would be 4. So what do you got? You got your height at your first sampling point. So f of C1, that's going to be your height at your first sampling point, times delta x1, that's your width. Well, what's height times width? It's area. So this is the area of your first rectangle, plus the area of your second rectangle, plus the area of your third rectangle, plus ... and then the area of your last rectangle. So what that is right there is exactly what we just got doing on number 17. We did 3 of them that were Riemann sums. We did L4, we did R4, we did M4, and ours looked just like this. We had f of negative 2 times 1, we had f of negative 1 times 1, we had f of 0 times 1, we had f of 1 times 1. We were writing out a Riemann sum, is what we were doing right there. Okay? So, this sum is called a Riemann sum for f on the interval AB. So anytime we do a height times width, height times width, height times width, R for Riemann, R for rectangle. Riemann sum is just adding up rectangle areas. That's all it is. A Riemann sum is just adding up rectangle areas. A lot of fancy language, but it's just saying that a Riemann sum is when you add up rectangle areas. All right. So, number 1, we're going to start your homework right here. You're going to do your homework here. Well, I'll tell you in a second your homework. But we're going to do 1 through 6 on your homework. We're going to do number 1 together. You're going to draw this picture 6 times for your homework. So draw it neatly. You're going to get to draw a lot of pictures here. So I hope there's no national intramural championship tonight or anything. Was that last night?
Semifinals.
That was just semifinals? Okay, so next week's it.
I think they're moving state districts.
The finals are on Wednesday next week?
Monday.
Oh, Monday.
Oh, but we're trying to move our games.
Oh, yeah. Well, we got a quiz next Thursday, so I'm just saying, you might want to leave Wednesday. We'll move it to Wednesday. All right. So those points, all these dots are kind of important here. Okay, so I got 1, 2, 3, 4, 5, and then this is -5, -4, -3, -2, -1. Okay, and this is 1, 2, 3, 4, 5. I think I went by ones there. Wouldn't that be right? What is this function? Oh, they don't even tell you. This is just the graph of G. 1, 2, 3. Yeah, it goes up to a peak at 3. Well, no, wait. No, the peak's a little above 3. Yeah, these points are right at 3. Okay. And this is -1, and this is -2. Okay, now they've got the picture there for you, so maybe you could overlay your paper on top, whatever, I don't know, but you want to draw a pretty neat picture of this because you're going to have it 6 times, okay, for problems 1 through 6. Now, you're not going to have to write out all 4 like we did on number 17, right? You're going to have one problem like number 17 where you have to write out L4, R4, and so that problem you'll have 4 pictures, and then here on 1 through 6 you're going to have 6 pictures. You're going to have 10 pictures overall on your homework. And then there's another 2 problems you're doing where you're going to write it out, but you're not going to have a picture. You have to draw a picture. Okay? All right, so number 1 says this is a g graph, little g, and this is the integral from -5 to 5 of g of x dx. Now, in some of the problems, they change those. Now, A says estimate the value by evaluating a left sum with 5 equal subintervals. So they want us to do an L5. Now, part B says to draw it. Now, to be honest, I think it's better to draw it first. If you're going to have to draw it, I think you should draw it before you actually write it out. But it doesn't matter, because on a couple of your homework problems, you're just going to write it out without drawing it at all. So you don't really need to have it drawn to write it out. Maybe we should practice that. So let's do that. Let's write it out without practicing it, or without drawing it. Now, if you've already got your picture there, it can be helpful to go ahead and do your subdivisions, right? So how wide are these going to be? 5 minus -5 divided by 5, right? Remember, it's b minus a divided by n. So it's 5 minus -5. So our total interval is 10, and we're going to do 5 subintervals. So 10 divided by 5 is 2. So our width, our delta x, is going to be 2 here. So we're going to start at -5, and then we're going to go to -3, and then we're going to go to -1, and then we're going to go to 1, and then we're going to go to 3, and then we're going to go to 5. So I like to put those back, I like to mark those, so I know, I like to make those nice and big and visible, so I can see what's going on. Okay? All right, so where's my first left rectangle going to be at? It's going to be at the left edge, right? -5. So it's going to be f of g of, thank you, yes, that's key. I want you using the proper notation. So this is g of -5 times 2 plus -3 times 2. So you see how you don't have to have it drawn, but it's not. Let me make this count. Look up here, please. Look up here. I know you guys are on hold. I will often, even if I'm not supposed to draw the picture for a problem, I will make myself an x-axis, and I'll go -5 to 5 like this, and then I'll divide it, and I'll go, okay, -3, and then it's going to be -1. Once I know the width is 2, I'll go -5, -3, -1, 1, 3, right? So I know where my subintervals are. So a lot of times I'll draw myself an x-axis. I don't care about the graph if I don't have to graph it, but I'll draw myself an x-axis and get my subinterval marks. Okay, plus what's the next one? G of -1 times 2 plus G of 1 times 2 plus G of 3 times 2, right? Now, let's go ahead and calculate that. Let's go ahead and write that out. So, what do you got? What's G of -5? -2 times 2 plus. I think it's a good idea to write this. If it was a quiz, I definitely would write this because you got partial credit. Maybe you just screwed up one of those numbers. G of -3 is 2 times 2 plus G of -1, 3 times 2 plus G of 1, 0 times 2 plus G of 3, -1 times 2. So that gives me -4 plus 6 plus 0 minus 2, cancel, total area of 4, right? So that's problem number 1. Now we got to draw the picture. So that's part A. Evaluate 5 left rectangles. And now we got to draw. So come in here. Go left 2. Excuse me, you're going right. I'm sorry. And there is, now that's way too much negative area, isn't it? The actual negative area is this black area in here, right? The actual area is that black area. So we got way too much negative. It's not a great, but it's never going to be with only 5 rectangles. Okay, now -3, we go up to the curve, and we draw over to -1, and then down. So we got that left rectangle. Then at -1, we draw up to the curve and across and down. And we got that rectangle. And then what about at 1? That's just 0, right? There's no area there. And then at 3, we go down to the curve and across all the way to 5. And there is that area. So those 5 blue rectangles, notice, and this is what I like about writing it out down here, this represents my 5 blue rectangles. First one's -4, second one is 4, next one is 6, it sure looks like it, the next one was 0, and then the last one was -2. Okay, I know that's a lot of writing out that for a pretty easy calculation, but you got to keep our goal in mind. Our goal is not to just calculate these 5 areas. Our goal is to see the pattern, see how it's written out, because what we really want to do is to do 100 left rectangles, 1,000 left rectangles, 10,000 left rectangles, right? That's what we really want to do. And we're not going to sit here and calculate 1,000, right? Back in the day when they came up with this, they didn't have the electronic power to just do it. So they had to teach, we really want a better approximation. We want 10,000 left rectangles. How can we do it? Well, let's see what 5 looks like, 10 looks like, 20 looks like. I see a pattern. Oh, let's develop some sort of formula. How could we calculate this, right? How can we do it to shorten that for us a little bit? That's where we're headed with this. Okay, so your homework is going to be, that was all of number 1. That was a picture, and then L5 is what it asked for, okay? That was on page 354. So this is section 5.6, starts on page 354, and so I don't know if this is what the assignment sheet says. I'm kind of switched around the assignment sheet a little bit. Yeah, I'm cutting a few out here. So it's 1 through 6, so you're going to be drawing, and we just did number 1, so you know what it's supposed to look like, and so a new picture for each one. Okay, now number 7, and I know I could have went 1 through 7 there, but okay. So, but 1 through 6 are the same, right? So 1 through 6 are the same kind of problem. Okay, number 7 gives you a graph, and it says estimate the integral from 1 to 7 using a right sum with 3 equal subintervals. So they want an R3, but notice it didn't say to draw. So at number 7, you're just going to do an R3, but you don't have to draw. You don't have to draw them. Now, if you want to, you can, but you're just going to write out an R3 and calculate, okay? And then we're going to do number 10. And on number 10, it uses that same picture, and they want you to do a T3. It says do a trapezoid with 3 equal subintervals. So same picture, but again, you don't have to draw a picture, right? You just crank out 3 trapezoids and write it out, just like we did back here, right? Write out your trapezoids. Okay, just like we did when we did number 17. And then the last problem on the homework is number 16. And that is just like number 17. That's like number 17 that we did together. So you are going to draw and write out L4, R4, M4, T4, right? That's when we did the x cubed. That's this one right here. That was the -2 to 2 x cubed dx. Okay? So on 17, and then you're going to compare that to the actual answer that you get using the fundamental theorem. So this one we did with the x cubed, where we do, now, so on that one, you're going to have 4 pictures, right? You need to have a picture for each one of those. Okay, so you're gonna have a picture for each one of these, and you're gonna have 4 pictures on number 16. And these you're gonna write out, but you won't have pictures. Okay, that's reasonable, that's not terrible. Because like I said, on the assignment sheet, it also says do number 25 and number 28, so I'm not quite sure why I'm going so easy on it. Like I said, I'm getting soft. If my former students saw this, they would be angry.
Maybe they're still using our function.
Maybe.
This is good.